So now as we begin our Module 13, we're taking a look at Chapter 10 in our textbook with the topic of columns. So within this module, we're going to discuss the stability of the structure, its ability to support a given load without experiencing a sudden change in configuration. In this discussion, we're going to be focusing on columns, that is the analysis and design of vertical prismatic members supporting axial compressive loads. So within this module here, we have a couple of objectives. So upon the completion of this module, you should have a working knowledge and be able to describe the behavior of columns in terms of stability. Look at Euler's formula for columns using effective lengths to account for different end conditions. Develop a secant formula for the analysis of eccentrically loaded columns. Use the allowable stress design for columns made of steel, aluminum, and wood. Provide a basis for using load resistance factor design for steel columns, and present two design approaches for the eccentrically loaded columns, and particularly taking a look at the allowable stress method and the interaction method. So as this relates to our textbook, this is going to be Chapter 10. The first module, we'll break this down in 13.1, will be sections 1 and 2 from Chapter 10, and for Module 13.2, this will be sections 3 and 4 from Chapter 10. So we'll be breaking this module down into two different sections, 13.1 and 13.2. For our module 13.1, taking a look at the topic of columns from Chapter 10, specifically looking at stability and eccentric loading. So within this, we'll be looking at the stability of different structures and talk about eccentric loading and the secant formula. So within this, some activities we'll be doing is going through our theory for the above topics here, talking about some of the governing equations, some practical applications, and then going through some problem solving. So now let's take a look at the topic of the stability of structures. So if we're dealing with the design of columns, the cross-sectional area is selected such that the allowable stress is not exceeded. So that falls back on this equation right here. We have the fact that our normal stress is equal to our pressure over area, and this needs to be less than or equal to or cannot exceed our allowable stress, or sigma sub ALL. We also know when we're talking about our cross-sectional area that our deformation needs to fall within the following specifications here. So we have our deformation, our delta is equal to our load times our length. As we can see over here, if we go back over to our diagram on the left, we have our pinned axial loaded column right here. So you see it's pinned at both ends. So you got a pinned at A and pinned at B. And you have your load coming straight down here. And you see that's constrained to go straight down over that. So our length here is our L, and our load is up here as P. So our deformation falls within the specifications here, that load times that length L all over. Now here's that area right there. A times our modulus of elasticity. All of this needs to be less than or equal to our specifications. So this falls within the specifications that were given for our deformation. So now let's think about this in practical terms. If we do what we see in the top diagram up here, this is pinned at B, this is pinned at A, we have this constrained load P coming down here, pushing on it. What's going to happen with the column? If it's pinned in both those locations and the load can't move at all, well then what's going to happen is you're going to see it buckle like we see here. So with the load applied, the column suddenly buckles rather than remaining straight. So it's going to bow out like we see here in the diagram on the bottom. So now as we continue on to the topic of the stability of structures, what we next want to consider is a model with two rigid rods connected at a point C by a pin and a torsional spring of constant K. So we can see down here, here's our torsional spring, here's our pin at point C, here's our rigid rod going from A to C, and another rigid rod going from B to C right there. So that's the model that we're going to be considering here. Now, after a small perturbation, we can see we come up with a relationship from 10.1 in our textbook. We have this restoring moment, which is our K, our spring constant K, times 2 times our delta theta. Well, this right here is our 2 times our delta theta, is this angle right here. So if we're looking down, if this is going straight line from A to B, we come up with this angle here. This is our angle right there of 2 times our delta theta. So this is the delta theta right here in between the angle between our line going straight down from A to B and then going from A to C as well as from A to C as well as from B to C. So those are our angle delta thetas there, and this would be our angle right there of 2 times our delta theta. And this is our restoring moment when we multiply that 2 delta theta by our K. So now let's go back to our diagram in the top left over here. We have part A and part B. So if the two rods and the two forces are P and our P prime are perfectly aligned, the system will remain in position of equilibrium, as we can see over here in part A. Now this occurs as long as it is not disturbed. But let's say it's disturbed and we move our C over to the right just slightly so that each rod then forms a small angle. So this is that delta theta that we talked about before right there and right there. That's that small angle that it forms with the vertical. So the question is, will the system return to its original equilibrium position, or will it move further away? So in the first case, if it returns to its equilibrium position, then it's said to be stable. Now, if it doesn't move further away, then it's said to be unstable. So then the next obvious question is, how do we determine of whether or not this two-rod system is stable or unstable? So we can take a look and consider some of the forces acting on the rod. So we come down here, what we do is we do our free body diagram of our rod AC. So with that there, we can see we have this load P here, we have this moment M down here, and we have our P prime down here acting at point C. So all the forces are going to consist of that P prime, and this moment. So what is this moment? This moment is going to be P times L over 2 times the sine of theta. So this is P times L over 2 times the sine of theta. So you get your load times the distance. There's your L over 2, but then we got to do our perpendicular distance. So that's where this sine of theta comes into play. And this is what's going to be known as our destabilizing moment. So with that, we know that the column is stable, which means it tends to return to its aligned orientation if the following conditions are met based upon this arrangement up here. So P times our L over 2 times our delta theta needs to be less than our K times our 2 times our delta theta. So we can see here that that means our destabilizing moment needs to be less than our restoring moment in order for this column to be stable. Now, if we consider the situation where we have the moment of the first couple larger than that of the moment of the second couple, then what happens is the system tends to move away from the original equilibrium position, which we can see in our diagram in the top left here. And if this is the case, then the system is said to be unstable. Now, the load, when the two couple balances each other, is called our critical load, or our P sub CR. So this is our critical load there, which is given to us by the following relationship that we have our P sub CR times our L over 2 times the sine of our delta theta is equal to K times 2 times our delta theta. Now that also brings up the fact that we can see up here in this original equation here where they said that the P times L over 2 times the sine of delta theta is equal to P times L over 2 times our delta theta. And the reason for this is because the sine of delta theta is approximately equal to delta theta when the displacement of C is very small. And this occurs at the immediate onset of buckling. So that then leads us to our equation we see here in equation 10.2, where we say P is less than our P sub CR, which is equal to 4 times K over L. And that comes from just simply rearranging this relationship here. So we divide our 2 back over the other side, see that our delta thetas cancel, and we're left with this relationship right here. So continuing on with that same model, we see we have our load P applied up top here, and we see after perturbation, the system is going to settle to a new equilibrium configuration at a finite deflection angle. So we can see that in part A. Here's our model column in a buckled position. There's our point C out here. We can see have this angle now of theta. And we can see over on part B, we have the free body diagram of just the rod AC. So for our free body diagram of rod AC, we see we have our load P applied right here. We have down here at our point C, we have our P prime, and we have this moment M. And now we can see this angle right here, our theta, which is between our vertical and our rod AC. Now we also see this has a length of L over 2. We know that the full length before we applied the load of this was from A to B was L, so half of that to going from A to C is going to be our L over 2. So now we can relate these back to these equations that we see here. We have this relationship, we have P times, there's that length of L over 2, times the sine of our theta, where again, this is our angle theta right here. This is equal to our spring constant K times 2 theta, again, that same relationship there. Now we can rearrange that, move it over, and we end up with now is we have P over L, P times L over our 4K is equal to P over our P critical, our critical load right there, which is equal to our theta over our sine of theta. Now we want to make a note that our sine of theta is going to be less than theta, and if that's the case right there, the assumed configuration is only possible if our P is greater than our PCR, or our critical load. Load needs to be greater than our critical load. So now we want to move on to the topic of Euler's formula for a pin-ended column. So we'll go back to that same pin-ended column we saw earlier within this module. As we return to that column AB, what we want to do now is try to determine our critical value for the load P, or what we've seen as our P sub CR. Now recall that this is the load for which the position that we initially start with ceases to become stable. So if our load P is greater than our P sub CR, or our critical load, then what happens is if the slightest misalignment or any disturbance will then cause the column to buckle into a curved shape, like we see in part A of this diagram in the top left. So as we're looking at these pinned end columns, we can think of this as a beam placed in a vertical position and subjected to an axial load. So that's basically what we have here, is we have this beam from A to B placed in a vertical position, and you can see an axial load, our P and our P prime, acting on this here. So this is similar to what we saw back in chapter 9, so we can proceed the same way. We can say we have this point Q that's going to be located some distance x away from our starting point right there, with that being the end of our beam at that fixed point at point A. Now we can figure out our deflection down here at point Q, and what this is going to be is this distance y. So this is going to be our deflection of point Q, which is some distance x away from the pin at point A. Now, the thing to know is look at our axes. We always want to define our coordinate system. So our x-axis is going to be vertical and directed downward, that we can see right there. And our y-axis is going to be horizontal and directed to the right, which we can see here for our y-axis. So again, defining your coordinate system, what's positive, what's negative, what direction they're going in, is going to be important for this. So next thing we want to do is draw our free body diagram for portion AQ. So we can look at this in part B of this diagram on our top left of this slide here, and we can see, okay, if we want to go from A to Q right here, we're going to have our load P acting at point A. Down at Q, this is out a distance y away from our pin in our y direction right there. We're going to have this load P prime acting at Q. We're also going to have this moment M right here acting at Q as well. So if we consider the equilibrium of this free body AQ, then we can find our bending moment, our M. So what is our bending moment about Q right here? So what is this value for M? Well, this is going to be force times perpendicular distance. So if we take a look at this here, according to our chosen sign convention, we're going to have a negative P times Y. So our moment is going to be negative Py. Now what we can do with this is we can go back to some of our governing equations. Particularly, we can go back to our equation 9.4 from chapter 9, plug in this relationship that m is equal to our negative Py. And we do that, what we end up with is this relationship shown here in equation 10.4 from this chapter. So 10.4 shows us here that we have our second derivative of y with respect to x, so our d squared y over dx squared. And this is equal to, there's our m over ei. So now we can relate this now to saying our m is a negative Py, so replace m with that negative Py from our moment relationship here from this free body diagram. So now the 10.4 says that our second derivative of y with respect to x is equal to negative P all over ei times our distance y here, where this is our distance y right there, which is that deflection that we talked about earlier. Now we can transpose the last term, and we end up with a relationship that we see here in 10.5, where we have our second derivative of y with respect to x, our d squared y over dx squared, plus now our load P all over ei times y, and this is equal to 0 when we transpose and move this back over to the other side of our equation in 10.4. So the solution for the assumed configuration for this can only be obtained if the following conditions are met. So we'll take a look at our first condition here from equation 10.11 in our textbook, and this expression is known as our Euler's formula. So this says our P is greater than our critical load, our P sub CR, which is equal to now our pi squared times EI all over our L squared. So we can go back up here. This is our L, is that total length right here, and we have our modulus of elasticity as well for whatever material that we're using for this. Now also we have our expression 10.13, which shows that our normal stress here is equal to P over A, which needs to be greater than our critical stress here, which is equal to, now we see this relationship here, we have pi times our pi squared times our modulus of elasticity times A r squared all over L squared A, which we can reduce down to this relationship here of pi squared times our modulus of elasticity, all divided by L over R squared. Well, what is this L over R? L over R is going to be the slenderness ratio of the column. So the length over our radius of gyration right there. So the minimum value for this radius of gyration should be used to obtain the slenderness ratio and the critical stress in the column. So now what we want to do is summarize and rewrite our governing equations we just saw from the previous slide. So for the value of stress corresponding to our critical load, which is our P sub CR, we have this relationship we saw in our equation 10.11, which says our load is greater than our critical load, P greater than P sub CR. This is equal to this relationship of our pi squared times our modulus of elasticity times I all over L squared, where L is that total length. Now we also have the relationship for our normal stress. So our normal stress is equal to our load over our area. Now this is greater than our critical stress, which is going to be P sub CR over A, where P sub CR is that critical load divided by A there. So from this, we now have a relationship that our critical stress here, our sigma sub CR, is equal to our pi squared times our modulus of elasticity times AR squared all over our LA squared, which we can reduce down and simplify to our critical stress that we saw in our equation 10.13, which is our pi squared times our modulus of elasticity all over L over R squared, where we saw that the L over R was our slenderness ratio. So with these equations and relationships, what we want to do next is take a look at our plot of critical stress. So we can see that in our diagram on the top left over here, where we can see on our x-axis we have this L over R, which we defined as our slenderness ratio. And on our y-axis over here, we have our sigma or our stress in units of megapascals. So if we want to plot out our critical stress, our sigma sub CR, versus our slenderness ratio for a structural steel, well, for that structural steel, we can come up with our modular elasticity, and this would be 200 gigapascals, and we could have our sigma sub y for that structural steel, and we know that to be 250 megapascals. So we can see, we can draw this out over here. So for the structural steel, we have that sigma sub y right there, our yield strength right there, coming across at 250 megapascals. We go over here till we intersect our curve here, which this is our critical stress, our sigma sub CR, given by our equation 10.13, where we have our pi squared times our modular elasticity from this modulus right here for our structural steel, all divided by our slenderness ratio, L over R, quantity squared. Now, one thing we want to note and keep in mind here is that we haven't taken our safety factor into account when we're plotting this out for our critical stress. Another thing to consider, if we're using our equation 10.13 to calculate our critical stress, and this comes out to be larger than our yield strength, or sigma sub y, then this value is of no interest. And the reason because is that would mean that the column will yield in compression and cease to be elastic before it has a chance to buckle. So now taking a look at this equation. So now let's take a look at this equation 10.11b. So for this, we can see that our critical load, our P sub CR, is equal to our pi squared times our modular elasticity times our moment of inertia, all divided by this new variable here, LE squared. Well, what is LE? LE is going to be our equivalent length. So LE is going to be 2 times our L. So if we go back over to our diagram here, we can see this is for our column with one fixed and one free end. So at the fixed end here from B to A, this is this length L right here. So for our effective length, what we're trying to do is relate this back to a pinned column that we have these relationships and governing equations for. So the effective length of a free end column of length L is going to be equivalent to a pin-ended column of length 2 times L. So that's what we can see over here in part B of our diagram. So what we do is we find, okay, if this was pinned here and we extend this down, so this is the midpoint here, this will be down here at our A prime now, where we'll have now a load P at top of A and a load P prime down here at A prime. Then this total length, rather than being L, which goes from A to B, now is LE, which is 2 times L as we duplicate this, kind of mirror it about this right here, the fixed end at B. So now moving on to our equation 10.13b and relating this column here for the one fixed end and one free end back to our pinned column for our critical stress, we have the relationship of pi squared times our modular elasticity all over our LE over R now, where before our L over R was going to be our slenderness ratio, so our LE over R is now going to be known as our effective slenderness ratio there, where again, we're subbing in that LE is equal to 2 times L based upon the configuration that we see over here in our diagram. So now as we're continuing on with our discussion for columns with other types of end conditions, we were comparing this back when we looked at our fixed end and one free end column to a pin end column. So with the pin-ended column, we had those governing equations for our critical load and our critical stress. And we saw that we could, for the situation in part A here, for the one fixed end and one free end, modify those governing equations for both the critical load and the critical stress by changing what our L was. So in this case here, it would be our effective length is what we're looking at now. Rather than just L, we're looking at our effective length here to relate it back to that pin-ended column. So for each of these situations, we have the effective length for the columns, and that we can plug into those equations to modify those relationships for each of these different types of columns with other types of end conditions. So we saw when we went through for one fixed end and one free end, our LE, or our effective length, was going to be equal to 2 times that L. Now if we have both ends pinned, So we have this situation right here. That was the case that we started off with, and that was our LE is equal to L. So our effective length was that L. Those were our governing equations there. That's what we're comparing everything to at this point. So now what if we have the situation where we have one fixed end and one pinned end? Well, for that case there, then our effective length would be equal to 0.7 times that value for L. And our fourth case here for a different type of end condition, what if both ends are fixed? So we see it fixed right up here, and we see it fixed down here at A and at B. Then our effective length, or L sub E, is equal to half of L, or 0.5 L. And we can use this information for this effective length to go back to those governing equations for our critical load and our critical stress. So now let's apply some of that theory and governing equations to a concept application problem. So take a look now at concept application problem 10.1. In this problem here, they tell us that we have a 2 millimeter long pin-ended column. So that's going to be very important right there, the fact this is pin-ended. And we can see this in our diagram off on the left over here. We have the pin-end connections there. This is going to have a square cross-sectional area. This is also important as well. So it's very crucial that we really pay attention to the wording in these problems. The fact that it said pin-ended column and square cross-section are really going to help us in our solution to simplify things down. They also tell us this is made of wood. So with that, with the material, they tell us that our modular elasticity is 13 gigapascals and our allowable stress is 12 megapascals. So pay attention to our units, gigapascals for our modular elasticity and megapascals for our allowable stress. And they give us a factor of safety of 2.5, and they give us the hint for the solution to calculate Euler's critical load for buckling. Now, what are they asking us to solve in this problem? They want us to determine the size of this cross-section, which is a square cross-section, they give us up there, if the column is to safely support two different scenarios. So in part A, if it safely supports a 100 kilonewton load, and in part B, if it safely supports a 200 kilonewton load. So we'll go through and solve this for part A first, and then continue on and repeat that solution, but now using a load of 200 kilonewtons for part B, and see how that varies our solution as we're trying to determine the size of that cross section. So now that we've had an opportunity to read through that problem statement, look at our initial diagram, understand what they've given us and what they're asking us to solve for, our next step is to create our setup page. So I've done this problem out by hand. So here's our setup page here. And we see this is concept application 10.1. So what given information do we have? Well, we know a couple things. We know it's wood, we know it's a pin-ended column, and we know there's a square cross-section. So even though those don't have numeric values associated with them, they are going to be important for our solution. So I'm going to write those down up top next to my given. Now I also have here my length. So this is where I want those four things. I want my variable name, I want my numerical value, I want my units, and I want how it relates to my problem. So I have all four of those. There's my variable L. Here's my numerical value of 2. Here's my units of meters. Here's how it relates to my problem. That's a length. Now I do the same thing over here. I have my modular elasticity. This is E. This is given to me as 13 gigapascals. And I have my allowable stress, sigma sub ALL, which is equal to 12 megapascals. And I have my factor of safety given to me as 2.5. Call that FS. Now I also have a simplified version of my initial diagram. I have my load P at the top. I know it's pin supported at the top and bottom. Top is C, bottom is D of that column there, and it has a length of L. So I can go back over here. I left these in terms of variables, so I can go back to my givens to realize that L is 2 meters. Now, what do they want us to solve for? There's two parts of the problem. I'm going to write them out separately. Part A, part B. For both of these, they want us to find the size of the cross-section if the column is to safely support, in part A, it safely supports 100 kilonewtons. In part B, it's going to safely support 200 kilonewtons. So now that we have the setup page created, we can now begin the solution to our problem. So now as we begin our solution to this problem, I want to deal with this separately, part A and part B. So for part A, we'll look at this. This is a load of 100 kilonewtons. So our P is equal to 100 kilonewtons for this. So we need to find our critical load. Now this is going to be found by using the relationship that our critical load, P sub CR, is equal to our factor of safety times our load P. So this is found by multiplying the factor of safety by that load that's given to us as 100 kilonewtons for part A in our problem. So P sub CR, our critical load, is equal to 2.5 for our factor of safety times that load of 100 kilonewtons. So P sub CR is equal to 250 kilonewtons. Now from there, what we want to do is use Euler's formula, which they told us in the problem statement we should be using for our critical load. So this is equation 10.11a in our textbook, where we have P sub CR, our critical load, is equal to pi squared times our modular elasticity times our moment of inertia all over L squared. Well, what we want to find out of this is our moment of inertia. So we want to solve this for I. So when we solve this for I, our I is equal to, now on our numerator now when we rearrange this to solve this for I, our critical load, our P sub CR, times that length squared all over pi squared times our modulus elasticity E. So we continue on with this Euler's formula, rearranged to solve for our moment of inertia. We have that relationship there where we know now our critical load is 250 kilonewtons. Let's convert that to newtons. So 250 times 10 to the third newtons. Our L is equal to 2 meters. And our modulus elasticity for wood that they've given us in this problem is 13 gigapascals. So let's convert that to pascals, which you recall are newtons per meter squared. So that's 13 times 10 to the 9th pascals or newtons per meter squared. The reason I want to do that unit conversion is so that I can put it into my formula that I found here from Euler's equation for that moment of inertia I. So when I plug in my known values to this here, I is equal to, for my P sub CR, come up here, that's 250 times 10 to the third newtons. This is times my L squared, where my L is equal to, in this case here, 2 meters, so that's 2 meters squared, when I plug that in there. All over on the denominator, we have pi squared times now our modulus elasticity, which is 13 times 10 to the 9th in units of newtons per meters squared. So we plug that in, we do out some unit analysis on this, and we say, okay, well, I have a newton here, and a newton here that'll cancel on the numerator and denominator. And say I have a meter squared on the numerator and a 1 over meter squared on the denominator, which would make us a meters to the fourth for our problem there, which is the units we should expect for our value for I. So I is equal to 7.794 times 10 to the negative 6 in units of meters to the fourth. So now that I have a value for I for a square shape, I know that my I is equal to a to the fourth over 12. So for my moment of inertia, I can go back to my tables, look up that square shape, and that's where I get this a to the fourth over 12. So I can say, okay, let's plug in for my I. I have 7.794 times 10 to the negative 6 meters to the fourth is equal to a to the fourth over 12. Let's rearrange that, solve for a to the fourth. A to the fourth is equal to 12 times my value for I here, 7.794 times 10 to the negative 6 meters to the fourth. Now I can take the fourth root of both sides of that, solve for A. A is equal to 0.0983 meters, or approximately 0.1 meters, or 100 millimeters. You really do want to pay attention to your units here. You're going to stay with millimeters, you're going to stick with meters. Just make sure you're consistent and that everything checks out when you do your unit analysis. So from here, what we want to do is take a look at our normal stress in the column. So our stress in the column, we have our normal stress is equal to our load over that area, that cross-sectional area. So for this case here, we know that our load given to us in part A is 100 kilonewtons. Our area is going to be, because it's square, our A times A, because those are both going to be the same for that cross-section there, which is going to be 0.1 meters times 0.1 meters, or our A is equal to 0.1 meters squared. So I can plug that back in to my equation for my normal stress. Sigma is equal to 100 kilonewtons divided by 0.1 meters squared. So I solve that out, plug it into a calculator, whatever you want to use, and sigma ends up being a 10 megapascals. Again, pay attention to units. This is in megapascals. When we look at this and compare it to our allowable stress in the problem statement, and our allowable stress in the problem was 12 megapascals. So therefore, our sigma is less than my sigma allowable, because 10 megapascals is less than our 12 megapascals. So therefore, with this here, this 100 millimeter by 100 millimeter, or 0.1 meter by 0.1 meter cross section is going to be acceptable for our case. So now we've answered part A. Let's move on to part B, where now our load is 200 kilonewtons. So if our load is 200 kilonewtons, we can still use that same relationship with our factor of safety to get our critical load. So P sub CR, our critical load, is equal to our factor of safety times the load that they give us, which is 200 kilonewtons. So P sub CR is equal to 2.5 times 200 kilonewtons. So our critical load is equal to 500 kilonewtons. Now we can still go back to that same governing equation, rearrange it to solve for our I value. So our moment of inertia is equal to our critical load times L squared all over pi squared times our modulus elasticity. Plug in our known values again. So I is equal to, in this case now our critical load is 500 times 10 to the third newtons times our 2 meters squared all over our pi squared times our 13 times 10 to the 9th in pascals, or newtons per meter squared. So again, we see the newtons cancel with newtons. Our meters squared over 1 over 1 over meter squared becomes our meters to the fourth when we do out our unit analysis, which is exactly what we expect for I. So I is equal to 15.588 times 10 to the negative 6 meters to the fourth. So from this here, we can go back down for a square shape there and say that I is equal to our A over 4 for that square shape, which we can look up in our appendices or the charts. And we can rearrange that and plug in our value. Well, now our I is our 15.588 times 10 to the negative 6 to the meters fourth, which is equal to A to the fourth over 12. So solve that for A. A is equal to now, A to the fourth is equal to now 12 times our 15.588 times 10 to the negative 6 meters to the fourth there. Take the fourth root of both sides. What we end up with this is that A is equal to 0.11695. So 0.11695 meters. So our A is equal to, our capital A for our cross-sectional area there is equal to a lowercase a, and A are two sides. So we can say that our area there is equal to 0.11695 meters squared. Plug that into our equation for our stress. So normal stress is equal to P over A. So in this case here, our P is given to us as 200 kilonewtons divided by that cross-sectional area, which is 0.11695 meters squared. We solve that out, and we find that our sigma is equal to now 14.62 megapascals. And let's pay attention to our units here. And now what we want to do is compare that to our allowable stress. So going back to our allowable stress, this was 12 megapascals. So therefore, our stress that we found now with this load here based on those dimensions is going to be greater than our allowable stress. So since the stress is greater than the allowable stress, these dimensions are not acceptable. So what do? Therefore, the cross-section must be selected based upon its resistance to compression instead. So we'll rewrite this out. Area is equal to, we'll resolve our equation for stress using our allowable stress here. Area is equal to our load over the allowable stress, which is equal to now to 200 kilonewtons over 12 megapascals. Solve that out. So our area is going to be 16.67 times 10 to the negative third meters to the meter squared. So A times A will give us that cross-sectional area, or two sides, because it's square, they're equal. So A times A is equal to 16.67 times 10 to the negative third meters squared, or A squared is equal to 16.67 times 10 to the negative third meters squared. Take the square root of both sides. A is equal to the square root of 16.67 times 10 to the negative third meters squared, which says our side is going to need to be A equal to 0.1291 meters in order to stay within that allowable stress. So those are the new dimensions for our side for this column if we have that 200 kilonewton load. So next we're going to discuss eccentric loading and the secant formula. Now if we're talking about eccentric loading, this is going to be equivalent to a centric load and a couple. So let's go over here to our diagram on the left. In part A, what we have here is a column with an eccentric load. So we can see this is an eccentric load. This is not over the center of this column here from A to B. You can see it's offset to the left. This load is offset to the left by this distance E. So as we mentioned here, this is equivalent to a centric load and a couple. So over here in part B, we can see now our load is centric. It's right there in the dead center of this column there at A, and down here at B, that's our P and our P prime. And then we're going to have a couple. So we have our couple right here. So we have our moment about A and our moment about B. So this gives us a column that has now both a centric load and a couple that makes it equivalent to our column over here with just the eccentric load. Now the question is, how do we define this moment? So we can see we got a moment about A and a moment about B over our diagram for part B here. Well, we think moment is going to be force times that perpendicular distance. So what is our force and our distance? Well, our force is going to be P and our distance is going to be E right there. So the moment about A is shown here as P times E, and same as our moment about B is going to be P times E. So that's how we define our moment about A and about B. So with the eccentric loading of a column, we want to ask ourselves about bending, deflection, and deformation. So bending is going to occur for any non-zero eccentricity. The question of buckling now is going to depend on whether the resulting deflection becomes excessive. Now, if we're talking about deflection, the deflection does become infinite in the case where our load P is going to be equal to our critical load, our P sub CR. So now this brings us back to our relationship that we saw from chapter 9, where we had that our d squared y over dx squared, our second derivative of y with respect to x, is equal to our moment divided by our modulus of elasticity times our moment of inertia. So now we have a relationship for M. M we've shown here to be equal to P times E, where this is our load P, and this is our displacement E off of the center axis of the column. This is given in our equation 10.22 in our textbook. So we can replace our M with our PE here. Pay attention to sign convention. We end up with now, this is now equal to a negative P times E, our load times that distance right there, all over our modular elasticity times our moment of inertia, EI. Now, relating back to our equation 10.6 earlier within this module, we can now see that for eccentric loading, we have this relationship here that Y max is equal to E times the secant of, now we have here our P, square root of P over EI times L over 2 minus 1. And this relates back to equation 10.28 in our textbook. And from this relationship, we can see that our Y max will be infinite when this relationship here, our square root of P over EI times L over 2, is equal to our pi over 2. So if we plug in a pi over 2 over there, this makes our Y max become infinite. So now if we want to discuss our maximum stress, we have this equation 10.33 from our textbook, where we have our sigma max, our max stress, is equal to our load over area times 1 plus, there's our Y max plus that distance E times C all over our R squared. So this again is equation 10.33. Well, we have a definition for Y max from our equation 10.28. So what we can do then is we can plug this relationship here in for our Y max. And we do that, this reduces down and becomes our equation 10.36 in our textbook, where our maximum stress, our sigma max, is equal to P over A times 1 plus EC all over R squared times the secant of 1/2 times now that square root of P over EA times LE over R. Now what this is known as is this is our secant formula here from equation 10.36 in our textbook. Now what the secant formula does is this is going to find the force per unit area. So this P over A, that's our force per unit area that causes a specified maximum stress, so that's our sigma max that we're defining there, in a column with a given effective, we call now our slenderness ratio, which is this LE over R, for a ratio here now where we have this new EC over R squared, where E is the eccentricity of the applied load. Now, since this P over A, we can see on both sides of this, it's going to appear on both members, it's going to be necessary to solve a transcendental equation by trial and error. And from this, then we'll be able to obtain a value for this P over A corresponding to a given column and loading condition. Now this equation 10.36, which we write down again here, this can be used to draw the curves that we see on this slide. So these curves make it possible for us to determine the load per unit area, our P over A relationship that we see here, which causes the column to yield for given values of those ratios that we just talked about, our LE over R, which is our slenderness ratio, and this ratio here for our EC over R squared. Now, for the case for smaller values of the slenderness ratio, the secant is almost equal to 1, so we can reduce down this equation 10.36 to this equation 10.37, and thus PA can be assumed to be, given by this relationship here, of our sigma max all over our 1 plus, there's that ratio there, of our EC over R squared. So let's take a look at these plots a little bit more closely. So in part A, we have this in US customary units, and part B is just metric units. And these are both showing the secant formula plots for buckling in eccentrically loaded columns based off this relationship shown here in equation 10.36. So we can see along our x-axis, we have this LE over R, which we recall again as our slenderness ratio. So this goes from 0 up to 200. And then we can see we have each of these curves, our Euler curves on this as well, for this ratio of our EC over R squared. So there's that relationship here to equation 10.36 for our EC over R squared. And that is going to be for each of these curves. So if this is 1, 0.8, all the way up to 0 for the top curve right there. So now that each of these curves represents that ratio there for our EC over R squared, whereas our value for our slenderness ratio, the LE over R, from this part of the equation is down here on our x-axis. Now what we can get from this is that P over A. So that's what we're looking for, is that ratio here for our load over area, units of KSI, and that's going to be our y-axis, this case here going from 0 to 40 for this material. So for this material here, we can see they give us our modular elasticity and they give us our yield strength right there. So our modular elasticity is 29 times 10 to the 6 psi, and our yield strength here is going to be 36 KSI. So if we knew our ratio here for our slenderness ratio, and we knew our ratio for our EC over R squared, we'd come up. So let's just say that this was 50. So we go up here and let's say that this was our 0.6, and we can come across over here and we can get a value over here of approximately 21 or 22 for our P over A in units of KSI. So then we'd have this value here that we could then plug into our equation 10.36. And that's the same thing over here in part B of this chart here, but now our units are just in megapascals right here. So we can see our E is given to us in gigapascals, and our sigma Y is in megapascals as well.